Hey everyone! Sorry it's been so long. This actually has nothing to do with the project itself. I just haven't had enough time to sit down for 3 hours and record a video. So here's how this video is going to work out. It's going to have 3 main parts. The first part is going to be the demonstration, where I'm going to show you some beautiful path trace clips that I have curated and found and created over the past 2 months. And the second part is going to be a theoretical explanation where I explain all of the complicated data structures and algorithms that we use. And the third part is going to be the technical talk where I'm going to show you the actual code in the GitHub repository. So that's enough talking. Let's go ahead and get into by far the most exciting part, the demonstrations. This is a post-editing Andrew here. I just want to apologize for everything being sort of cropped off and also my face cam being in a weird place. This is my first time recording anything on my laptop and its aspect ratio isn't quite normal, so it was a little bit difficult to get it into a normal video aspect ratio. So it's still running back there in the background, so if my talking is really boring, just look over there. But now it's time for a theoretical explanation of how the code works. Okay, so first we're going to go over the octree structure, and I'll explain what that is in just a second. Essentially, an octree is a way of partitioning this grid into a hierarchical structure, and I'll get into what that means here in just a second. Let's go ahead and create a little sample scene. So essentially, our octree is going to partition this little design here into a hierarchical structure. And the way it does this is it starts with the highest level, which we'll draw out like this, which we'll call node A. So he is node A. Node A corresponds to, part of my bad drawing, but but it corresponds to the outermost box inside of the scene that we are trying to draw. Inside of node A, it splits it up into 4 nodes. In this case, it's a quad tree. Oct would mean 8, quad means 4, but the concept is exactly the same in either dimension. And another important part of this is called the Morton order, or Z-curve. It's just a way to partition the 3D space in such that you can loop over a 2D space in a one-dimensional array. That's really overcomplicated for what it's actually used for in this. Essentially, it's just we have quadrants 1, 2, 3, and 4, and this would be 5, 6, 7, and 8, and it would continue on like that, but we don't have to worry about that for right now. So essentially, we split up node A into its 4 quadrants, and then we look and we say, okay, does node 1 have anything in it? In this case, it doesn't, so we're not going to worry about that. The very top left quadrant of node A is finished. We're not going to go look into node 2, and we're going to say, is there anything in there? Nope, so that one's finished too. We're not going to look into node 3, and we're going to say, okay, this one does have something inside of it. So our octree is going to split that up, and it'll come back to it later, and it'll worry about it in a minute, but it's going to go ahead and go into node 4 and say, okay, same thing here, it has stuff. Then it's going to go back into these 2 nodes, which we will label as node B and as node C. And we'll go ahead and split it up over here as well. It's going to look inside of these nodes, and it's going to say, okay, is there anything in here? No. Is there anything in here? No. Anything in here? No. But in this one, we do have something. And in this case, that is the actual voxel that we are trying to represent. So this would be called a leaf node, because as on a tree, the leaf is sticking out and it doesn't have anything branching off from it. It then goes into the next quadrant and performs the same checks and finds that all of those are leaf nodes. And I'm going to go ahead and label these with a yellow. But this, and this are all leaf nodes. They would be A, B, C, D, E, F, and G. Okay, so now let's go over how this is translated into memory and how it's actually stored. Part of my horrible drawing, but this should get the job done for explaining how it works. Essentially, each node has 3 parts to it. It has a valid mask, it has a leaf flag, and it has a relative child pointer, or RCP for short. So let's go ahead and translate node A into its actual representation. Essentially, we're going to use this thing over here, which is going to tell us how to create our valid masks based off the quadrants. Each number represents to the quadrant, and essentially all we do is it looks at node A and it says, okay, is quadrant 1 full? No. So it's going to be a 0. Quadrant 2? Nope, it's another 0. Quadrant 3 does have stuff in it, so it's going to be a 1. It's going to be another 1 for quadrant 4. It then repeats this for all of the nodes that have children, which in this case are only nodes A, B, and C. So B would be 0, 0, 0, 1. C, it would be 0, 1, 1, 1. And for the leaf nodes, we don't actually need to store a valid mask because they don't have children, so there's no point indicating what children they have. And we also don't need to store a leaf flag because all the leaf flags tells us is, are the children of this current node, are they leaves or not? So for node B and for node C, this would be a 1 because yes, its children are in fact leaves. For node A, this would be a 0 because its children aren't leaves, they have children. Our relative child pointer tells you how far down in memory you have to go to get to the next one. So in this case, to get to its first child, which would be node B, from A, we would only have to move 1. And this would get us to whichever one this one is, which this bit corresponds to this node, this bit corresponds to this node. And the way it works is it's always stored in sequential order. So this is 3 and this is 4 in our valid mask and in our quadrant thing down here. And that lets us, if we know how many this has, which has 2, and we know how to get to there, which would be by 1, then we can go 1, and we know that it has 1, 2. Those 2 are its children, and then anything else is not its children. And for these, because there are no nodes that actually correspond to this, it's just the leaf nodes, these are simply 0. And in theory, we could get rid of the leaf flag entirely, because this will always be 0 whenever its children are leaves. But it's working fine without it right now, so that's a future optimization that I would like to make. And this is stored in, for a little bit of the technical stuff, we use uint32, I don't remember how it's actually spelled, but we use unsigned 32-bit integers to store it. Our relative child pointers, 23 bits, leaf flags are 1, and that leaves, I think, 8 bits for the valid mask, which would need 8 bits for 3 dimensions. So that is how it converts this grid into our octree structure in memory. I'll leave a few links to some of the resources I used to figure all this out. One of the main resources was a paper by Nvidia. It's a really good paper that I recommend you read. It also goes into a lot of explanation about other stuff that I have not implemented in this engine, but I highly recommend you check that out. I'll also leave a couple of links to other resources in the description that I think are pretty useful. Alright, so I'm going to move over here and we're going to explain the ray marching algorithm. This is arguably more important. Well, not really, because you need the data structure, but it's very important, and it was the main focus of the engine so far. So to demonstrate this, we'll take our scene from earlier, which looks something like this, and we are going to create a ray over here that is going to be casted into the octree, and we want to find where does it first intersect this geometry. And this can be done with a few functions. Push, pop, and advance are what they are called in the Nvidia paper, and it's what I've named them in my code as well. So let's do a quick definition of them. Push is responsible from, let's say you are in a higher level, coming out of that higher level, going into an even lower level node. Pop does the exact opposite. It goes from a low level node, and it pops, and it goes out to a higher level node. Advance, all it does is, let's say we are in this node here, it'll move us to the adjacent node. And I'm blocking that, but I'll move over here. So we'll get into that in a little more detail once we start demonstrating how it's going to ray trace through the scene. So first, our ray is going to look at this outer box, and it is going to say, okay, which quadrant do I first intersect with? Which is this quadrant. So it's going to go into here, and it's going to do a push, which is going to bring this over here, and now we are looking at just that quadrant. And it's going to say, okay, there's nothing in that quadrant, so it's just going to pop right back, and then it's going to move the ray to the end of that box because it knows there's nothing else inside of there. And now what it's going to do is going to do our advance function, which is going to say, okay, we are done with this quadrant, let's go ahead and move into the next one. So it's going to figure out which side it exits this quadrant from, and it's going to move into the adjacent quadrant. So it moves into this adjacent quadrant, and advance automatically performs a push for us. And this push is now going to look here at this node. And we know that it's going to hit there, but the way it figures that out is it looks here and it says, okay, we are here, we're going to look inside of here, we're going to push inside of here, nothing there, so it's going to move over, it's going to try to advance, and when it tries to advance into that next one, it's going to say, oh look, that is a leaf node, we have found it. And that is how, I move back up here, that is essentially how the algorithm works. It's just a series of these push, pop, and advance functions being ran over and over again until it finds until it finds the data. And this allows for it to very efficiently make use of the hierarchical data structure that we have implemented. One more data structure that we are going to cover very briefly, because it's not very good, it's kind of just something I made up when I was trying to hopefully get colors implemented, is our voxel type data, is what I have it called. Essentially, each voxel, or scene, stores two things. It stores its ID, and it stores its data. Currently I have it set up to store color, and technically it is also set up to store per voxel normals, I believe, but I don't actually use those in the rendering. Essentially, this data, it's just 32-bit integers, whatever you want them to be. And this ID is related, actually it is, this Z order thing that we brought up earlier. Essentially, the way the ID works is, let's say we have another grid, right? And this one is 1, 2, 3. Okay, the ID is essentially what number it is. So let's say it's this one here, its ID would be 13. So it would be 13 for the ID, and then whatever, say like an RGB value that it would want to store or something, whatever data we decide to have it store. But that's essentially how it works. And it is then sorted based off of its ID in incrementing order. And that allows for us to perform a binary search, which I'll go over briefly as well. Essentially, if we have a list of numbers from 0 to 20, and they're in sequential order like such, we can find a number by looping over it, which is a very, very slow operation. Or, because we know they're sorted, we can first split this into half, check this middle one. Let's say we're trying to find the number 2. We would check here and say, okay, is this number 2? No. Is 2 less than this number? Yes. So we're not going to check anything greater than it. Then we're going to go about halfway here, and you can see it splits right there between 2. So maybe you would check for 3, and we'd say that this 2 is in fact less than 3, so it's not going to be any of those. And that leaves 2 numbers left, so it'd probably end up picking 2. And there we've only done 3 checks in comparison to however many checks it would have taken for a much, much larger array. Okay, that was a lot of talk. I'm really sorry about all of that, but hopefully you've got something out of it and have a deeper understanding about how this works. There's another data structure that I've implemented that I'm pretty proud of, but I'd say it's better to explain that with just looking at example pieces of code. So we might get into that later in the technical explanation, which we're about to go into, but that's not for right now. Yeah, let's do the technical explanation. Here it is running. You can see it is running pretty well too. It's at about 15 milliseconds per frame or so currently, and this is rendering it at full 1080p. So it's definitely within the realm of real time. It drops down to around 30 milliseconds per frame or so in a couple of situations, but overall I'd say this is very, very usable for a lot of things. So there are still a couple of visual improvements I would like to make. This is one of them. I don't know why that happens. I have a feeling it's because, no, I do know why that happens, but that's not an issue with the engine itself. It's the engine it's an issue with the path tracing implementation I have set up, which we will look at. So this is an example use of the code. This is really all that's important to it. The rest of this is just stuff getting it set up. Essentially, I have this function here, which loads in a vertex shader and a fragment shader into a shader program. And see, I'm doing that for quite a few shaders here. And then we are passing them to our render frame function, which if we go look at the render frame function, you can see it has a couple of pretty simple functions to just render fragment shader to target buffer, which takes in the shader and it outputs it to a frame buffer. And we have a couple of these functions that all do similar things, or they'll have different things that they do. For example, I have an octrees wavelet filter set up that is really simple. All I do is I give it 2 buffers, and I tell it how many times to iterate, and I give it the shader that it needs to iterate, and it outputs the output of that to this buffer. I have a couple with 2 inputs. There's really a lot of things that you can do with it already, and these are super easy to create new ones too, which is really nice. Here you can see an example of how our buffer system works. We essentially, I define these up here. This is a really badly programmed demonstration, by the way. I just kind of put this together pretty quickly so I could demonstrate it. If we look here, we are declaring a project v frame buffer instance. And so let's look at frame buffer 1, or FBO1. You can see we create frame buffer object advanced. The advanced is just left over from when I was changing the way that they worked and I had 2 frame buffer systems at once. And you give it the width and the height of the frame buffer, and then you can add whatever texture you want to it. So you call the add texture to frame buffer and you feed it an FBO1, you tell it the format, and you tell it the name. The name is used for whenever you're reading it, so if we don't actually do it in there, but here in octrees denoiser, whenever we have it as a sampler 2D, or a texture being fed into the shader, we can read from it with that name. So in this case, it prepends input buffer, and if it's input buffer 1 or 2, and then it's the name that you specify. So that's indirect light. And then this is just the format. And yeah, it works really quite well for everything. Whenever you call these functions, it automatically handles whatever you give to it. So it's a pretty modular system in my opinion, and I'm quite happy with that. So this is, again, just a little demonstration, and you can see here, this is all the code for the path tracer. This is all the code that the user would actually have to write. In reality, if I zoom out, this is all in one fragment shader. This is all responsible for the rendering and for a couple of other functionalities that I have built into it. So there's quite a bit that goes into it. You can see this GLSL shader is almost 1,000 lines long. Let's go ahead and look at the actual code itself, which we'll do that on GitHub actually. So let me pull up the GitHub. Here it is. So this is the project v GitHub. It's been up, like I said in the beginning, for about 2 months. I just haven't been able to get around to recording it. And we've got a README going. And also I should clarify that this is my first time ever doing a C++ or any project on this scale. And this is also my first time ever open sourcing a project. So if there's anything in here that you guys think is bad, or if you want to change it, feel free to. I am very, very aware that there's a lot that I'm probably doing wrong. Anyways, back to the GitHub repository. I've got the goals, some basic steps to install it and set it up, an explanation on the modular structure, which we'll get into in just a second. And yeah, it's pretty good. We've got a code of conduct. This is just from GitHub's one of their template code of conducts. We've got the MIT license copy over here. Let's go ahead and get into the code. First, we're gonna look in the source. We've got 3 files. We've got core, or 3 modules, I guess is a better way to put it. We have core, we have graphics, and we have utils. Utils is responsible for what I explained at the beginning of the video, which is creating our data structures. And graphics is responsible for all the stuff that I showed you in that path tracer. And core is really simple. It's just responsible for creating a window and handling some basic user input that is not very well designed right now, but hopefully it gets better in the future. So let's go ahead and look in core first, since it's the simplest and it's just pretty simple. This is all it is. I mean, we have a function for moving the camera. We have a function for creating a window and an OpenGL instance, and that's literally all it is inside of there. Inside of graphics though, this is the wrong branch, give me a second. It's under advanced rendering currently. If we go back in here, we go to graphics, we can see this, there we go, it's quite a bit longer, but essentially we've got this add texture to frame buffer function. I guess I should explain what the frame buffers are. That might be a good idea. Let's go to our include, and if we go inside of graphics.h, we have our frame buffer right here. A frame buffer contains its width, its height, a OpenGL buffer ID, and a vector of this texture struct. This texture struct has the OpenGL texture ID, the OpenGL texture format, and the name. And these two things are what you were seeing in that path tracer one. I was talking about all the frame buffers and textures. And we've got this function that can add a texture to the frame buffer, and that's a system that I'm quite happy with and proud of. I developed it a couple of weeks ago. So yeah, that works well. I am, in general, pretty happy with the way that this project has turned out. I think it looks great, and it runs pretty well too, all things considered. Overall, I am very happy with this project, and I hope you guys are interested and would like to help contribute. I will leave a link to the GitHub repository in the description, as well as any resources that I use to make this video. And yeah, I'll see you all in the next one. Goodbye.